Chapter 7 and 8, Section 2, Part 3. In this part, we'll have a chapter. So in Chapter 8, we'll see how we can generate random variate from a specific distribution. The objective of this chapter, Chapter 8, is learning a procedure for sampling or generating the random variates from a specific distribution, which could be a continuous or a discrete probability distribution. Okay, and the method that we are going to learn in this chapter is called inverse transform technique. So there are other methods in chapter 8 of the textbook, but we're going to learn just this method. Okay. So these slides are coming from chapter 2, so you're familiar with these slides. So let's review these ones first, and then we'll have actually more examples. Actually, I can say the main concept of the inverse transform technique has been introduced in chapter 2. So I'm reviewing those slides and then we'll have more examples. So when we talk about a random number, it will be a number between 0 to 1, and we randomly generate that number in the interval of 0 to 1. And then if we want to generate a random variable or a random variate from a specific distribution, at first we need to obtain the CDF function of that distribution. Okay, so if you obtain the CDF function of that distribution like this, let's say in general, then by equalizing the CDF with a random number R, then we can solve that equation for X, which we call this as XR. Then that XR will be a random variate generated from that distribution. Okay, so this is the general approach here, which is called inverse transform technique. Okay. So, for example, for a continuous distribution, at first we need to find the CDF of the distribution, right? Fx. So, for example, let's say our distribution is exponential distribution. So this is our PDF function. Then the CDF will be this, right? So now if we generate a random number between 0 to 1, let's say R in Excel, for example, we can do this by the rand function. And then we set the CDF function be equal to that generated random number. And then we solve this for X. As you see here, we're obtaining the inverse function of the CDF. And this is why we call this method as inverse transform technique. Okay, and for this example, for exponential distribution, X becomes this. So yeah, by having a random number and this equation, we can obtain a random variate from exponential distribution. Okay. And for discrete, again, the same. At first we obtain the CDF of that discrete distribution, and then we have a random number, and then again we set the CDF be equal to R. But since here we don't have a continuous equation here, and we have just the intervals and the numbers, so we will find an interval between xi minus 1, let's say, to xi, in which that R lies between that interval for the value of the CDF function. And then we consider the upper limit of that interval xi as the random variate here for that discrete distribution. Okay. For example, here, let's say we have this empirical discrete distribution. So the fx, the CDF, can be calculated in the second row here. So we have 0.24, 0.39 up to 1, right? So if we generate a 0.65, we'll see that that 0.65 lies in between these two numbers, right? And the upper limit, which is 24, will be our random variate for this random number. And if we have another random number, let's say 0.05, and as you see here, it lies between 0 up to 0.24, then again the upper limit, which is 15 here, will be our random variate for this discrete distribution. Okay, and yeah, for normal we can use this function in Excel. So let's go ahead. So here we have more examples for uniform distribution. As you know, this is the PDF of the uniform distribution, right? And this will be, so at first, again, we obtain the fx or CDF of the uniform distribution, and then we set the fx be equal to a random number, and again we solve this equation for x, and so we have this equation for generating a random variate from a uniform distribution. Okay, and if we have the viable distribution, again this is our PDF, and so the CDF will be this. So again we set the CDF to be equal to R, and then solve that equation for x, and so by having this relationship we can obtain a random variate from viable distribution by having a random number. Okay, and for triangular distribution, here we assume that we have a triangular distribution between 0 and 2. So 0 is here, here is 1, and here is 2. Okay, so for this distribution, triangle distribution, we have the PDF like this, based on that figure that I have here. So the CDF for a triangle distribution becomes this. For this example, as you see here, we have two intervals, right? Sorry, we have 4 intervals, but we are going to deal with just the 2 ones, not this one. Two intervals. Okay, so for x between 0 and 1, we have this equation. Okay, and for x between 1 and 2, we have this equation. So if we solve these two equations for each individually for each interval for x, we can obtain x value by this. So here, as you see here, again, we have 2 intervals based on the intervals of x. We have 2 intervals for the random number. So if we generate a random number first, and if it's between 0 to 0.5, we will use the first equation, this one, in order to obtain the random variate from that triangular distribution. But if the random number lies between half and 1, then we will use this, the second equation here, to obtain a random variate from the triangular distribution. Okay, and so we are done on these 2 chapters. As I said, in chapter 8 includes other methods as well, but we are just covering the inverse transform technique in our course. Okay, so yeah, we are done on chapters 7 and 8. Okay, thank you.